Good morning students, how are you? I hope you are fine. So first let me clear one doubt. Before my class reconcile colors completed, so in that many students they asked where we have to download that link. What is your link? That is one doubt. And this class for that is JEE, NEET or KSET. So two doubts mainly observed. So this class for JEE, NEET and KSET, all upcoming second PU students. Okay. And next one is I also provided one link for you, that is just you need one Google account, that's it. Okay, I given that I uploaded it Google Drive, just Google link is there, you can click that. Okay, before first complete class you observe, after finishing class just you download that link. Okay, download that notes, full notes are given, because before this after starting these online classes many students some my students they call me, we are hostless, with us notes not there, then and textbook also not there, no books, then what we should do? That's why no need to worry, we provided complete notes. Just listen this class and download that link, then there you are getting notes. Along with the notes I given practice sheet also. Okay, because for entrance, now this class for theory entrance, theory and entrance for all the students. Okay, and actual the problem is running chapter is coordination compounds, that chapter actually not completed, right? That chapter not completed, and in KSET in some sections D and F block chapter there. So to avoid the confusion, after coming to college we can cover that D and F block chapter and the coordination compounds. To avoid that problem, now I am going to start new chapter, that is the solid state. Okay, solid state. In our track this is the next chapter only according to schedule, solid state. I hope are you able to watch. So solid state, this chapter, in solid state what are the different types of solids and how to find the formula of solids, what are the defects in solids and how to calculate the density, like this different electrical property, magnetic property, all this we are going to discuss. Okay, shall we start? So solid state, any matter that exists in three physical states, majorly, not only three, majorly exist in three physical states: solid state, liquid state and gaseous state. Okay, solids, how to decide this is solid, this is gas, this is liquid? In 8th and 9th standard we learned that solid state, any matter that has that has definite shape and also that has definite volume. Okay, any matter that has a definite shape and definite volume, that is called solid. Solid state has definite shape and a definite volume. Liquid state means that has definite volume but no definite shape. Nothing but in beaker some water taken, half liter. So for example in beaker water up to this came. Okay, same water in another. Now its volume is 1 liter. Same water in another beaker taken, 1 liter only. Nothing but that liquid has definite volume but there is no definite shape. Okay, and gaseous state means there is no definite shape and no definite volume. For example, some gas in one beaker, then it occupies full volume, and same gas in another beaker, it occupies full volume. Nothing but solid state that has definite shape, definite volume. Liquid state that has a definite volume but no definite shape, and gaseous state no definite shape and no definite volume, based on these three physical states. Now what is the first question is what is the favorable condition for that solid state? The matter can exist in solid state. At what stage that can exist in solid state? What are the conditions? Two conditions only. One is interactions, another is the temperature. At low temperature matter can exist in a solid state. Okay, at low temperature is the favorable condition. And second one is the interactions. What is this interaction? Between the particles, like these particles. What are these particles? Not laddus. These are if it is a sodium atoms. If it is sodium chloride, Na plus and Cl minus. If it is ice, H2O molecules. Okay, these particles are called constituent particles. Now here in this chapter we are using constituent particles. Constituent particles means they are atoms or ions or molecules, whatever be it is. In that solid, what is that? Okay, for example, this is a sodium solid. Okay, now sodium atoms, all these sodium atoms are closely packed with each other. Okay, Sodium atoms are closely packed with each other. So strong interactions are there. Like this strong interactions are there, then it is a solid state. If particles are closely packed with each other and strong interactions are there. Nothing but before corona, in each bench 4 members, close interaction, strong interactions are there, close packing, then that is a solid state. But now distance is more. Now we are like gaseous state. One particle is here, another particle is here. So distance is more, interactions are less. If interactions are negligible, then that state is a gaseous state. Less interactions are there, that is a liquid state. Strong interactions are there, then it is a solid state. So in solid state, strong intermolecular interactions are present. So depends on interactions and also depends on temperature. Okay, depends on interactions and temperature. What is the favorable condition to exist in solid state? Like this question given, what we should mark? Strong interactions and low temperature. These two conditions are favorable conditions. Okay, strong interactions required and low temperature, then substance exists in solid state. Now in this chapter we are learning only solids, not liquids and gases. So come to the solids. If strong interactions are there and temperature is low, matter exists in solid state. This is the first point. Okay. Now, what are the different types of solids? Now we are learning the first concept is what are the different types of solids. So solids majorly divide into 2 types. The first concept is different types of solids. So solids are divided into 2 types. Crystalline solids and amorphous solids. Crystalline solids and amorphous solids. So the first concept in this chapter is the classification of solids, types of solids. 2 types of solids, crystalline solids and amorphous solids. And while listening, no need to write any running notes because I provided full clear notes, that is your Pooja Didi notes, very clear handwriting. Okay, so no need to write anything, just listen and observe because it is complete 3D and imagination. Okay, crystalline solids and amorphous solids. What are the characteristics? Nothing but differences between crystalline solids and amorphous solids. So what are the characteristics of crystalline solids and what are the characteristics of amorphous solids? Many points are there, many differences, but each point first we should understand. Okay, then we can learn that easily. Okay, so now crystalline solids. In crystalline solids, all constituent particles are arranged in regular order. Okay, all constituent particles are arranged in regular order. In amorphous solids, irregular arrangement. First point, what is the regular arrangement? Irregular arrangement. For example, sodium chloride crystal. Okay, sodium chloride crystal, Na plus Cl minus. Okay, and next one is Na plus Cl minus, Cl minus Na plus, Cl minus Na plus and Na plus Cl minus. Like this, all particles, one cation, one anion, one cation, one anion. Any direction you observe like that, Na plus Cl minus. Like this we are getting, not diagonally, don't observe. Na plus Cl minus are arranged in alternate position. Nothing but one regular arrangement is there. This structure name is, already in D and F block elements we learned. D and F block elements have FCC structure, CCP structure, HCP structure. FCC, face centered cubic, nothing but one definite crystal structure is there. Like that arranged, that is regular arrangement. Na plus Cl minus, Na plus Cl minus arranged in alternate position. Okay, like this alternate position exact arrangement is there, that is called regular arrangement. So in crystalline solids, all constituent particles are arranged in regular order. Come to amorphous, for example rubber. Okay, in that rubber, organic compound, carbon chains are present. Okay, this chapter in polymers we are going to learn anyhow. Carbon chains are present. Now these carbon chains are linked by sulfurs. Here sulfur links are present. There is a 1 sulfur, 2 sulfur, 3 sulfur atoms, different positions, no exact position. Here 3 sulfur link, here 2 sulfur link, and after 2 carbons, after 3 carbons, after many carbons, no exact arrangement, that is the irregular arrangement. So constituent particles are arranged in irregular order, that is amorphous. All constituent particles are arranged in regular order, that is the crystalline. Okay. In crystalline, all particles are arranged in regular order. In amorphous, they are arranged in irregular order. So because of this regular arrangement, we are getting exact shape. Instead of shape, we can use geometry. Instead of geometry, we can use structure. Instead of all these 3, in this chapter we are using one more new word, that is the crystal lattice. Crystal lattice. So all crystals, they have definite crystal lattice. Crystal lattice is nothing but structure. They have definite structure. Okay, definite crystal lattice. Here no definite crystal lattice. Because of regular arrangement, we are getting exact structure, that is called crystal lattice. No crystal lattice in amorphous. So crystalline solids have definite crystal lattice. In amorphous, no definite crystal lattice, because here regular arrangement is there, here irregular arrangement. Okay. Next character is, because of regular arrangement, here clean cleavage is possible. In crystalline, clean cleavage is possible. In amorphous, that clean cleavage is not possible. No clean cleavage. What is this clean cleavage? See this, well known. Okay. Now here it is one crystalline. It is a cubic, nothing but in 6th standard you learned, I think, that is the all edges are equal. Okay, A equal to B equal to C. Now this is a cube. Now this is one large crystal. For example, it is NaCl. Its structure is cubic. Okay, I given. Now I break this into small pieces. Each piece also cubic. Yes or no? Each piece structure is also cubic. Nothing but clean cleavage is possible. Large structure is a cubic, and we cut that into small pieces. Each piece has that cubic structure. Nothing but NaCl, sodium chloride salt. That's a common salt. Large common salt taken. Its structure is FCC. You cut into small pieces. Tata salt powder. That is not amorphous. That is also crystalline. Small pieces. That each piece structure is also FCC. Crystal salt you take, its structure is FCC. Powdered salt you take, its structure is also FCC. Nothing but after cutting also, then there is no disturbance in structure. Nothing but clean cleavage is possible. Clean cleavage is possible means without disturbance we can cut into small pieces. Like that here not possible, because regular arrangement not there. After cutting, cubes we are getting or any other we are getting. So clean cleavage is not possible in amorphous solids. Here clean cleavage is possible. Okay. After clean cleavage, again observe this. Here we can get a plane surface. After clean cleavage, plane surface we have, because clean cutting is possible. So crystalline solids have plane surface. I given in notes all these points. Clearly you can read that. So plane surface. Here plane surface is possible, and here clean cutting is not possible first of all. So no plane surface. Okay. In crystalline solids, plane surface is there. In amorphous solids, no plane surface is there. And here, to identify these positions, here this structure we can identify by passing X-rays. In physics also you learned, I think, by passing X-rays we can find the crystal structure, that is crystallography. Okay, X-ray diffraction. In periodic classification also atomic size is identified by using X-ray diffraction. You learn now? So this structure we are finding by using X-ray diffraction. Nothing but X-rays are passed on this, different planes are there. So diffraction with definite angle takes place. Exact arrangement is there, then that X-ray diffraction is possible. Where that regular arrangement? Crystalline. Okay, that's why here only X-ray diffraction is possible. Okay, where X-ray diffraction is possible means in crystalline solids. Regular arrangement is there, clean cleavage is possible. So we are getting plane surface, then X-ray diffraction is possible. So X-ray diffraction is possible in crystalline solids. Here irregular arrangement, that's why no X-ray diffraction. Okay, no X-ray diffraction in amorphous solids. Crystalline solid shows X-ray diffraction. Here plane surface is there no plane surface. Here clean cleavage is possible, here no clean cleavage, because they have definite crystal lattice, here no definite crystal lattice. Why they have definite crystal lattice? All the constituent particles are arranged in a regular order. So regular order, definite shape is there, then that is the crystalline solid. So this crystalline solid is called true solid. And this is called pseudo solid. Pseudo means false. Okay, pseudo solid, false solid. Pseudo solid or super cooled liquid. I hope you are able to understand my handwriting also. Pseudo solids, super cooled liquids. They are called pseudo solids or super cooled liquids. Why they are pseudo solids? Solid already definite shape, definite volume. Definite shape is there, that is called solid state. Here definite shape, but here no definite shape. So how can we say these are solids? That's why they are called pseudo solids, because they have solid characters and liquid characters also. Super cool liquid. What is the meaning of this? Why it is called super cool liquid? In the 9th standard you learned that a glass is called super cool liquid. Which is super cool liquid? That is a glass. Learn no? So why it is called super cool liquid? Olden buildings, there if you observe window glasses, top portion is very thin but bottom portion is thick, opaque. Why that bottom? New buildings complete glass is transparent like that, but old buildings glasses you observe, window glass especially, their top is thin, bottom is thick. Why it is thick? Glass flows slowly, nothing but it has a diffusion, like slight rate of diffusion is there. It can diffuse like liquid, that's why it is called super cool liquid. Okay, so the question is old glass buildings, window glasses are old buildings, window glasses, top portion is thin, bottom portion is thick because of given. What's the answer? Glass can flows. It is amorphous. Slight rate of diffusion is there. That's why it is called super cool liquid. That is the meaning of this one, super cool liquid. Why it is called pseudo solid? There is no exact shape. That's why it is a pseudo solid. So crystalline solids are called true solids. Okay. And next one is come to the next. In crystalline solids, long range order is there. Long range order. And amorphous solids, short range order. Which of the following has short range order? Given answer is amorphous solids. What is this long range order, short range order? Okay. Long range order throughout the crystal, same arrangement, starting Na plus Cl minus, Na plus Cl minus, last also Na plus Cl minus. Throughout the crystal, anywhere you observe no disturbance in structure, exact arrangement is there. Complete crystal having perfect arrangement, nothing but that is a long range order. Short range order means for example here after 10 disulfide link we are getting, again after 10 disulfide link we are getting, nothing but regular order. But immediately after 20 trisulfide link we are getting, nothing but disturbance started. Most of the students 50 minutes can concentrate in class, total 50 minutes can concentrate, starting how they are listening, last minute also same concentration, that is long range order. Throughout the class same concentration we are maintaining, but maximum students first 5 minutes they will concentrate more, then finally last 5 minutes they won't concentrate, that is a short range order. So long range order means perfect arrangement throughout the crystal. Short range arrangement means sometimes regular we are getting, sometimes irregular, nothing but full substance not in exact structure, that is a short range order. So which one has short range order given? Amorphous. And long range order given, that is a crystalline. So crystalline has long range order, amorphous has short range order. And next, in crystalline they have sharp melting point. Sharp melting point. Amorphous range of melting point. Differences for every point I am giving reason. With reason if you learn you can remember long time, like long range order. Okay. Now this is a sharp melting point. Next is a range of melting point. What is this sharp melting point? If it is crystalline, that substance A, its melting point is a 56.8 degrees centigrade. with points exact temperature we can give. At this temperature only melting takes place. Before this, even at 56 degrees centigrade also no melting, nothing but that has the exact melting point. Why this exact melting point? Exact structure is there, regular arrangement is there, perfect structure is there, perfect melting point also there. So crystalline solids have sharp melting point, but amorphous, for solid, one example, solid B, that is the amorphous solid. Its the temperature is its melting point 60 degrees to 100 degrees centigrade. Like this we are giving. In bracket like this given its melting point means there is a range. In this range anywhere melting takes place because there is no regular arrangement. So because of irregular arrangement here range of melting point, and because of regular arrangement here sharp melting point. So which one has sharp melting point given? Crystalline solid. Which one has plane surface given? Crystalline solid. Which one has the range of melting point given? Amorphous solids. Where perfect structure is present? Crystalline solids. Perfect structure is present, that is a crystalline solid. Where X-ray diffraction is possible? Crystalline solids. Where clean cleavage is possible? Crystalline solids. Questions are like this only. The following having sharp melting point. The following has plane surface. In following X-ray diffraction is possible. Just we have to learn characteristics of crystalline and amorphous. Okay. Now these have sharp melting point and here range of melting point. And next one is in crystalline solids. Now these are anisotropic. Crystalline solids are anisotropic in nature. Amorphous solids are isotropic in nature. Isotropic in nature. Crystalline solids are anisotropic. Amorphous solids are isotropic. What is the meaning of this anisotropic and isotropic? Okay. What is the meaning of clean cleavage? We can cut without disturbing the structure. What is the plane surface? After cutting exact plane surfaces we are getting. Surfaces are clear. And next because of plane X-ray diffraction also possible. And why they have sharp melting point? Perfect structure is there. That's why sharp melting point. Now the next one. What is that long range order? Throughout the crystal same structure. Now next one is anisotropic, isotropic. Okay. What is this anisotropic nature? Anisotropic. Now some physical properties. This is very important point. Some physical properties like refractive index or conductivity like this. Okay. Not all the properties. Some physical properties. Na plus. Now it is a crystalline solid. Na plus Cl minus, Na plus Cl minus. And Cl minus Na plus, Cl minus Na plus, Na plus Cl minus, Na plus Cl minus, Cl minus Na plus. Enough no 4 lines. Cl minus and Na plus. Okay. Now here complete regular arrangement is there. Now it is the crystalline solid. Actually NaCl amorphous not there, but anyhow for example I am giving that. Na plus amorphous means irregular arrangement. Na plus Cl minus, Cl minus, Cl minus Na plus, Na plus, Cl minus, Cl minus, Cl minus, Na plus, Na plus. For example like this given. That is the irregular arrangement. Just for example, that is the amorphous. This is the crystalline. Okay. Now anisotropic, isotropic. Some physical properties, for example conductivity we are observing. Conductivity in this direction. Now we are getting conductivity answer from Na plus and Cl minus. Now which are responsible for this conductivity? Na plus are responsible, Cl minus also responsible. Next, in this direction we are observing. Na plus are responsible, Cl minus also responsible. In this direction we are observing. Now conductivity we are getting only because of Na plus. In this direction we are observing. Conductivity we are getting only because of Cl minus. Okay. But in amorphous, in this one more line, third line, Na plus, Cl minus, Cl minus. Okay, like this given total 4 lines. In this direction we are observing conductivity because of Na plus and Cl minus. This direction because of Na plus, Cl minus. This direction because of Na plus, Cl minus. And this direction because of Na plus, Cl minus. This direction Because of Na plus and Cl minus. Nothing but in all directions we are getting same. Na plus is responsible, Cl minus also responsible. So in crystalline solids, because of regular arrangement, some physical properties like refractive index or conductivity changes with change in direction. Changes with change in direction. Okay, the property changes with change in direction. But in amorphous, in all directions we are getting same. In all directions, that is because of Na plus and Cl minus. So physical properties like refractive index or conductivity changes with change in direction. That nature is a anisotropic nature. So which are anisotropic nature? Given that is a crystalline solids are anisotropic in nature. And in all directions, physical properties like, not all the physical properties, that's why we are using physical properties like some physical properties like refractive index, conductivity similar in all directions, then that nature is a isotropic in nature. So crystalline solids are anisotropic in nature, amorphous solids are isotropic in nature. Crystalline solids have short melting point, amorphous solids have range of melting point. Crystalline solids have long range order, amorphous solids have short range order. In crystalline clean cleavage is possible, amorphous no clean cleavage. And crystalline plane surface is there, amorphous no plane surface. Crystalline shows X-ray diffraction, but in amorphous no X-ray diffraction. Crystalline having definite crystal lattice, amorphous no crystal lattice, because crystalline have regular arrangement, amorphous irregular arrangement. Finally, crystalline solids are true solids and amorphous solids are pseudo solids or supercooled liquids. Then examples, crystalline, many crystalline are there, no need to practice. Examples for amorphous, now I am giving examples: rubber, plastic, starch. These are repeated examples, starch and wood. Examples for, and gelatinous aluminum hydroxide. Gelatinous aluminum hydroxide, these are examples, common examples, many examples, all examples I mentioned there, you can collect that. So these are repeated examples: rubber, plastic, wood, starch. Examples for amorphous solids. Now entrance question, one more thing, now what I am explaining, this is a theory plus entrance. Again separate entrance explanation not there, and practice sheet also complete entrance only. 20 questions in each practice sheet. Daily just you have to practice 20 questions. Read the notes, no need to read any other. That notes is more than enough. Okay, just read that notes 20 minutes and solve those 20 questions. 20 minutes not required, 20 seconds enough. Now I will ask one question. How they will ask questions related to this classification differences between crystalline and amorphous. The following solid has short range order. I am not writing full question. The following solid has short range order. Options here: rock salt. Remember common names, no? Rock salt. Second one, gypsum. Third one, plastic. And fourth one is ice. Which one has short range order? Just we have to observe, in given options one is amorphous, remaining 3 options definitely crystalline, because we have to mark only one option. So one is amorphous, remaining 3 are crystalline. So here rock salt, NaCl, well known, ionic, that is the crystalline. Anyhow, what I given examples here: rubber, plastic, starch, wood, gelatinous aluminum hydroxide. These are repeated examples. Almost they will give options from these only. So now I given one option, that is the plastic. Plastic is the amorphous. Then answer is the plastic. That's it. That is a short range order. This is about differences between crystalline solids and amorphous solids. Clear? And next one is come to the next topic. Is it clear? So the next topic is types of crystalline solids. What are the different? Full chapter types of only. First one is the types of solids. 2 types: crystalline solids and amorphous solids. Second one is the types of crystalline solids, because solids are true solids, crystalline only. So full chapter we are going to discuss about only crystalline solids, not amorphous. Just amorphous, just for general knowledge only. So now crystalline solids. What are the different types of crystalline solids? Now based on nature of constituent particles. What are constituent particles? Atoms or ions or molecules, any one constituent particle. For example, NaCl, Na plus Cl minus are constituent particles. Sodium crystal, only sodium atoms are constituent particles. Ice, H2O molecules, same I am repeating, same example, H2O molecules are constituent particles. So we are using one word, that is the constituent particles. Okay. So based on nature of constituent particles, crystalline solids are classified into 4 types. So what is the fourth type? Atoms, ions, molecules. One more is there. So now what are the 4 types? Ionic crystals, ionic crystals, covalent crystals, metallic crystals, molecular crystals. Here also very easy to identify the characteristics. Only the thing is that we should practice examples. Some examples are there, those examples we should practice. Then almost in options also examples only they will mention. Direct option, ionic crystal, covalent crystal, they won't mention examples. So we should concentrate on examples: ionic crystal, covalent crystal, metallic crystal and molecular crystals. What are these ionic crystals? Here constituent particles are ions. If ions are the constituent particles, Na plus Cl minus, like this ions. Ions are constituent particles, then that is called ionic crystal. Okay. If atoms are constituent particles, for example diamond, that is a crystal. Okay. In diamond which particles are present? All carbon atoms only present. So complete carbon atoms. So if atoms are constituent particles, they are called covalent crystals. Metallic crystals. What are these metallic crystals? Especially metals we are taking. In metals, in chemical bonding learned, metallic bond. What is that metallic bond? So what happens here? One metal, for example sodium. Sodium crystal. In that what are the interactions present? First sodium loses electron, it changes to Na plus ion. Now free electron is there. Like this many sodium atoms, they lose this. Why sodium loses electron? That already we learned in periodic classification, because sodium has a low ionization energy. That's why it loses electron easily, like that much we learned. Learn no? Sodium, low ionization energy, it is a metal, so it can loses electron, so it changes to Na plus ion. Now Na plus ion formed and loses electron. Now this electron negative charge and sodium ion positive charge. Opposite charges, they are bonded by electrostatic interactions. Nothing but ionic bond, electrostatic interactions. So electrostatic interactions will develop between these free ions, that is only electron C, free electrons, and these ions. That bond is nothing but metallic bond. This we learned in chemical bonding. What is that metallic bond? What is that electron C? Okay. Now what are the constituent particles? These metal ions only constituent particles. Nothing but these metal ions are called metal kernels. Remember no? These are metal kernels. In metallic crystal, metal ions will form. Those metal ions are called metal kernels. Metal kernels and free electrons also there. Okay. And molecular crystals. What are the constituent particles? Definitely we can answer molecules. If molecules are constituent particles, they are called molecular crystals. If metal kernels are constituent particles, they are called metallic crystals. Nothing but metal positive ions. Okay. If atoms are constituent particles, they are called covalent crystals. If ions are constituent particles, they are called ionic crystals. This is the first. What are the constituent particles? Okay. And many years back in KSET we given that question. In covalent crystals, the constituent particles are like that only given. Just what is the answer? Atoms. Atoms are the constituent particles in covalent crystal. Okay. Next, what are the interactions? What are the interactions between these? Ions are bonded by ionic bond. Ionic bond means electrostatic interactions. So here what are the interactions given? Electrostatic interactions. And here covalent bond. Covalent bond means there is nothing but sharing of electrons. So what are the interactions? Sharing of electrons. here what are the interactions? Again metal kernel positive and free electron negative. Positive and negative, what are the interactions? Electrostatic interactions. But not two ions, one is the free electron. So electrostatic interactions. And here interactions between molecules given. For example, H2O, chemical bonding again. Between H2O molecules, which type of interactions are present? Hydrogen bond chance there. Or CO2. It is a polar or non-polar? How to decide? Based on dipole moment already learned, we can identify dipole moment equal to 0, that is non-polar. If dipole moment not equal to 0, then it is a polar. Okay, now it is a non-polar. So non-polar means which type of interactions are present? Van der Waals interactions or induced dipole interactions. That type of interactions are present. If it is polar, for example HCl. Which type of interactions present between HCl molecules? Given that it is a polar interaction, because it is a polar covalent compound. So the interactions are dipole interactions. So in molecular crystal, which type of interactions are present? If that given answer for that, here hydrogen bond possibility there, dipole interactions possibility there, and induced dipole, London forces, Van der Waals forces, like this interactions are present. Okay, and here only electrostatic, here sharing of electrons, and here electrostatic. Here all of these answer definitely, because different types of interactions are there. These are interactions in different types of crystalline solids. Now come to the strength. Here electrostatic interactions. Okay, definitely these are hard ionic crystals. And here sharing of electrons, that two maximum covalent crystals, they exist as giant polymers. Diamond exists as giant polymer. So giant polymers. So these are very hard. Crystalline solids, covalent crystalline solids are very hard, except that graphite, because graphite is soft because of layer structure. In 14th group we learned. Okay, because of layer structure graphite is soft. Except graphite, definitely in bracket we have to take, except graphite they are very hard. And here metallic. D and F block elements recently we learned, they are hard, but S block in first year we learned, they are soft. Yes or no? So S block metals are metallic solids, D and F block metals also metallic solids, but some are soft, some are hard, that depends on strength of the metallic bond. That's why here general hard, soft, two chances there, hard or soft, because S block and D block different. And these are generally, definitely here weak attractions, Van der Waals interactions and dipole interactions, this type of interactions weaker than these. That's why these are soft solids. Okay, molecular solid anyone given, they are soft solids. Metallic given, they are soft or hard, two chances there. And covalent crystals are very hard, ionic crystals are hard. Okay, based on this strength. Now melting points, which one having very high melting point, like that question given. Now hard means definitely they have high melting point, very hard given, very high melting point, hard or soft. Generally we are taking most of the solids, metallic solids, they are D and F block only. Hard given means high melting point, or low also we can take high melting point. General statement now we are taking, they have high melting point. And here molecular low melting point. So the question is which of the following has low melting point? This example is a molecular. Which molecular given that has low melting point? Which one is soft solid? Option is a molecular solid. Molecular solid is a soft solid and that has a low melting point. Okay, these are characteristics of different types of crystalline solids. Now come to the last one, is there is a conductivity. Which are good conductors, which are bad conductors? Now ionic crystals, free ions are there, then they are good conductors. Can we say like this? No, not possible, because here ionic solid, for example NaCl solid, all Na plus Cl minus are closely packed with each other, no free ions, nothing but there is no mobility of ions. If there is no mobility of ions, then it is bad conductor. Nothing but ionic solids are bad conductors in solid state. Okay, ionic solids are bad conductors in solid state, but in molten state, molten means a hot liquid state. In liquid state, this changes to Na plus and Cl minus. or simply aqueous solution given. In aqueous solution, if it dissolve in water, that decomposes to Na plus and Cl minus. Nothing but free ions are formed. Now it acts as a good conductor. So the correct option for ionic crystals, they are bad conductors in solid state but good conductors in aqueous solution and fused state or molten state. So here what is the point here? They are bad conductors in solid state but good conductors in a fused state and also in aqueous solution. Instead of fused state, what we can use? A molten state. Okay. Now come to covalent. Any free ions? No. Because atoms are constituent particles. Any free electrons? No. No ions, no electrons. So these are bad conductors. But except again graphite. Because graphite already we learned the hybridization is sp2, trigonal planar, each carbon has one unpaired electron, then graphite is a good conductor. That's why again in bracket here I given that graphite good conductor, except graphite remaining all covalent solids are bad conductors. So general statement, these are bad conductors. And metallic, they have free electrons, so they are good conductors. So which of the following crystal solids are good conductors? Given answer, metallic crystals. Which are good conductors in aqueous and fused state only? Given answer, ionic crystals. Which are bad conductors? Given, these are bad conductors. Here also no electrons, no ions. Definitely these are bad conductors. Able to see this? So bad conductors. So here covalent molecular crystals are bad conductors and ionic crystals are good conductors only in aqueous and fused state, and metallic crystals are generally good conductors. Okay. Next here examples. Only the difficult task is remembering those examples. So examples we have to remember as the covalent and molecular enough, because the ionic anyhow we can identify. Metallic we can identify. Any metal given, that is a metallic solid only. So what are the examples for covalent solids? Here examples, diamond, repeated examples now I am giving. These are important examples. Diamond, graphite, full no need to write now, half of written you can understand. Graphite, okay, anyhow, full. Diamond, graphite and carborundum. What is the formula of carborundum? Common names, because now you are free at home, so practice all the common names. Many common names anyhow given. Silicon carbide, its common name is a carborundum. What is corundum? Don't confuse, that is a Al2O3. This is the carborundum, silicon carbide. And silicon, this silicon given, it is also covalent. And aluminum nitride, boron nitride. Okay, these are examples for covalent crystals. These are repeated examples. At least these examples you should remember. Okay, and molecular crystals. What are the examples for molecular crystals? Sulfur, phosphorus, iodine, nothing but all halogens, fluorine, chlorine and all noble gases in solid state. They are molecular solids. Helium, neon, they are noble gases. Again you are giving example here, we can convert gas to liquid, liquid to gas, solid. Okay, in solid state, helium, neon, these are examples for molecular solids. And ice, H2O, dry ice. What is the dry ice? Solid carbon dioxide. These are repeated examples for, anyhow in almost all the materials one common example is that there is a I2. The following is molecular solid. No, question is not the following is molecular solid. The following is a soft solid given. The option is a NaCl, silicon and sodium, or here anyhow copper, all metals we can take, and one more option is I2. Then answer is definitely here, just we have to check which is molecular solid. That molecular solid is soft solid. So the question is the following is soft solid. Options are sodium chloride and silicon and here copper or sodium, and there iodine or phosphorus given. Then we should mark iodine or phosphorus. Nothing but if we practice the examples we can answer. Options they won't give ionic, metallic, covalent, molecular, like this they won't give. Options always examples only. Understand that? Options only examples. So definitely we have to practice example. So the one more question, for example, the following has low melting point. The following has low melting point. First option dry ice. Second option K2SO4. Third option Fe. Fourth option is SiC or carborundum, like this given. Then in these four options just we have to check which is molecular solid. Which is molecular solid? Ice, dry ice. that is molecular solid. Just that is the answer. Okay. So these are characteristics of different types of crystalline solids. I hope it is clear. Okay. Come to the next topic. Till now it is like introduction only, like names. Now original story. Start the story. The first one is the types of unit cells. What are the different types of unit cells? So from this, that imagination required. So listen carefully. Don't waste time with other chatting other. So avoid that. So concentrate here. What are the different types of unit cells? Types of unit cells. What is this unit cell? First we should know that what is unit cell, then different types of unit cells. What is this unit cell? For example, come to this. What is the structure of this? It is a cubic structure. To identify the structure full, we have to pass X-rays. Many X-rays we have to pass, then we can find the structure. Instead of this, one small portion we are taking. Okay, this small portion structure is a cubic. If this small portion structure we identified, full remaining repeated, no, same type, cubes only repeated. Now full, what is the structure given? We can answer cubic. To find this structure, we have to pass X-rays. Full crystal structure no need to find. Just one small piece we are taking. The small piece structure we identified, same pieces will repeat in that. Same pieces repeat. So same structure is repeated. This small piece structure, for example, it is FCC. Full crystal structure is also FCC. We can conclude that its structure is a FCC. Okay. The smallest repeated three-dimensional unit. This is the three-dimensional. The smallest repeated three-dimensional unit of crystal that gives whole crystal structure. For example, we plan to purchase one cake. To taste that cake, just we have to eat one small piece. No need to eat full cake. Okay, the small piece taste, how that remaining full cake taste also similar. So to find the taste of the one cake, one small piece is enough. Okay, otherwise rice cooked or not, just one piece, one we have to observe. It is cooked, total rice cooked. Okay, like that, to find the structure also, it is a complex structures. To find the crystal structure, just one small piece we have to take. The small piece structure is similar to whole crystal structure. The smallest repeated three-dimensional unit of crystal that gives whole crystal lattice structure. Clear? The smallest repeated three-dimensional unit of crystal that gives whole crystal lattice structure, that is unit cell. Okay, what are the different types of unit cells? Almost time. So types of unit cells in tomorrow's episode we can learn. So tomorrow's episode is a very important. Types of unit cells, how to find the particles, how to calculate the formulas. So very interesting episode. So don't miss it. Stay home, stay safe. Okay, take care.